The topic of GraphRag has emerged to be quite interesting in the RAG world right now, and essentially it boils down to involving a knowledge graph as a data structure in your RAG retrieval pipeline. The reason we do this is because, frankly speaking, the data we're working with nowadays has more importance on the relationships than the data points themselves. And modeling these kinds of data sets that we work with in real life, such as networking or computational chemistry or social networks or transportation, modeling these in a relational database can be a bit tricky, especially when you start dealing with table joins. So ArangoDB was introduced to solve that problem, to offer a seamless way to traverse through your data set using the power of graph. Graph is kind of a key component right now with large language models because it allows you to introduce graph algorithms and simple concepts such as breadth first and depth first search traversals across your data sets. And the power of this is better combined when you store metadata on your nodes and your edges. So not only do you have individual nodes, but you also have data points available on those nodes as well as the edges. So this can be a powerful tool for combining vector similarity with the ability to match, let's say, your top 4 or top 5 chunks and traverse the knowledge graph associated to that chunk to fetch more context to the LLM. So at this point, I'll take a second to introduce ArangoDB. As mentioned, we started in 2013. We are open source on GitHub with about 14,000 stars. The code base was built in C++ and the UI is in JavaScript. And our multi-model comes from the ability to offer nodes and edges as a common data structure for your data points. You can just use ArangoDB just as a document database, similar to Mongo. Of course, native JSON with key value pairs and 3 different mechanisms for search. Geospatial, full text, and vector search, most recently vector via the implementation of FICE. So you can now create IVF indexes within ArangoDB to perform approximate nearest neighbor on your vector embeddings. This is not all through separate API. This is all through one API and one query language. It's called AQL, Arango Query Language. And for those coming from an SQL background, it's quite similar. Of course, scalability applies to both vertical and horizontal, which means that you can scale your graph to n number of database servers. So essentially creating a distributed graph charted across multiple servers, with, of course, the ability to scale the individual server to CPU and memory. Yeah, so if you've never heard of us, we are not affiliated with MongoDB. We do sound similar, but Arango is actually just a type of avocado. So yeah, no affiliation whatsoever. Right, so let me quickly talk about GraphRag. As mentioned, during the retrieval phase, it goes beyond just performing vector similarity to retrieve your chunk embeddings. It's about using those chunks or using your search start as the starting point to traverse a complex graph. And that could be using a variety of traversal mechanisms, breadth first, depth first, or applying graph algorithms on the subgraph associated to the neighborhood or the neighborhood associated to the matched chunk. From a data ingestion perspective, it looks a bit different. So traditional RAG pipelines will use a large language model during the retrieval phase to summarize or finalize the answer, whereas GraphRag also requires a large language model during the data ingestion phase. We'll get to that in a sec, but it's essentially taking your chunks, your text files, and having an LLM through a carefully crafted prompt template, of course, extract the relationships that matter to the user. The components for this, so you need, of course, the concept of a data model that can be represented as a graph. You need the concept of search, whether that comes from embedding similarity search or full text search. And the benefits, of course, outweigh the the extra work involved, because essentially you have additional context that you can provide to a large language model, and it enhances the quality. Now, I don't need to prove this myself. There are many papers and industry use cases and companies that have already done this for us, from papers dating back to January of 2024 or even late 23, talking about the power of combining a knowledge graph with large language models. Most notably, of course, Microsoft GraphRag, kind of taking the world by storm with their framework around building a knowledge graph, applying Leiden clustering to form communities, summarizing those communities, and then offering two different retrieval mechanisms, one that target the node embeddings and one that target the communities that you've generated, creating kind of like a global versus local search mechanism. NVIDIA, of course, combining LLMs and knowledge graphs. There's a few blog posts that I highly recommend and am willing to provide after that come from NVIDIA. Now, the input looks like this. So you're dealing with a PDF file, a PowerPoint slide, a CSV file, any kind of text that is considered unstructured in the sense that it is not machine interpretable. You take the same chunking strategy as you normally would by separating your text into multiple chunks. During that phase, you employ a large language model to extract relevant nodes and edges that belong to those chunks. So you're essentially creating mini subgraphs across your data set. At which point during the final stage could you then merge the graph, apply a graph algorithm such as clustering, or perform entity resolution to disambiguate your entities, to then create a finally merged knowledge graph. The result looks like this from a database perspective. You have documents that represent your nodes, which have been extracted by the large language model. And then you have, of course, your edges that point to that node. So here's an example of one node, which is extracted as chapter 2 or module 2 of the PDF. And then here's another node called vaccine cold chain. And then there's the edge representing the relationship between these two nodes over here. Now notice you now have access to embeddings on 3 different levels. You have node embeddings, you have edge embeddings, or I'm sorry, that's not an edge embedding, that's a second node embedding. And then you have your edge embedding at the bottom here as well, referring to this one. So those are your first 2 embeddings. And of course, just like in a traditional RAG system, you have your chunk embedding available as well. And that creates essentially a knowledge graph composed of 3 different types of embeddings at 3 different levels of granularity, just with a simple concept of extracting triplets. What this allows you to do is to take a question that can be complex as the one mentioned above, and to have a variety of different search start options. You can decompose the query, extract entities relevant to the query, and search individually based on those embeddings. You could choose to start from the chunk and explore the neighborhood of that chunk and emphasize, based on the cosine similarity of the edge embeddings, emphasize which relationships to return or to highlight relevant to that chunk. You could start from the nodes and traverse, again, via edge similarity on your way to finding a golden path of nodes and edges that make up your answer. You can incorporate a large language model to serve as a judge for every hop you make within the graph to ask if this is enough information to answer the query, the initial question of the user. So there's a lot of techniques you can apply simply because you've created a graph that you can now traverse over your for your query. Now, from a OPEA perspective, this has been made extremely easy for us to deploy, because what OPEA has done is created microservices for you to deploy and manage. These become almost like a Lambda function, if you will, that serve as a piece to plug into any end-to-end application you're building. For us, we exist in what's called the DataPrep and the retriever service, which were mentioned in the previous talk, I believe. And for us, the DataPrep service is just a means to create a knowledge graph out of your unstructured data. That could be Google documents, Word documents, PowerPoint slides, PDF files. We take responsibility in, given the large language model and embedding model you want to run. We take the chunk, we do take care of the chunking and the entity extraction, and then the storing in ArangoDB. And then on the other side, once that graph is created, we provide a way for you to retrieve the relevant chunks or the relevant nodes and edges to formulate the final answer for the large language model. And this can combine a variety of different search tools, right? So vector search being the entry point, but then you can combine this with keyword search, because we do have a search engine built into Arango as well. You could use the graph traversals. So essentially what you're doing is you're using ArangoDB truly for its multi-model capabilities. You can use it as both a vector store, a graph database, a document database. Yeah. So we find that this GraphRag wave, or this emergence, is truly making an impact on the databases that are truly multi-model. So we're very proud to be a part of this. The microservices I'm referring to you to are part of this GenAI comps repo, which I highly recommend you check out. Lots of really cool things that ArangoDB isn't a part of, but really cool things across the board that OPEA is offering. So from a end-to-end solution perspective, OPEA manages a second repository called GenAI Examples, which offers the mega services that you can use to deploy those microservices along with other pieces. So the best place to test this out would be through ChatQnA, which is their chatbot-based solution that allows you to work with text files and use natural language to query them. On the right-hand side, you'll see a YAML specification of what is required to deploy ChatQnA. And it's actually, OPEA has made this very simple for us. It's really just defining a set of DataPrep and retriever microservices along with the database selected, a set of model hosting solutions, so text embeddings and VLLM, and then the ChatQnA backend and UI. All of this can run using a YAML specification like this and take advantage of Intel hardware for model hosting. Right, so I think at this point I can quickly exit the window just to give you an idea of what that graph looks like in detail. What you see here is just a visualization of a graph. In fact, the same graph I showed you about the medical document I was referring to, just immunization practices. It's a random document I picked up. The equivalent graph looks like this in ArangoDB. Now, this is just a sample of the graph, around 60 nodes and 75 edges, but you can start to see what kind of entities have been extracted from the LLM. So hepatitis B being marked as a specific type of node. If I click on it, it allows you to say, okay, this is a disease. It has an embedding of dimension, 768. It has an edge pointing from hepatitis B to the vaccine of hepatitis B. And of course, that relationship is the vaccine protects against hepatitis B. So these are all things that have been extracted from, using a large language model. Now, I can go on and on, but we can traverse the graph a bit and say that, okay, the vaccine was mentioned in multiple sources. In other words, it was mentioned in multiple chunks, and those chunks, of course, have embeddings at our disposal. And I could continue to traverse. So you can start to visualize how this would look like if you had a query embedding. You could start from hepatitis B if it was related to that query. You can traverse to the vaccine clause, then you can go to the chunk related. You could choose to go in another direction based on the similarity of your edges. So lots of opportunity here for retrieval. Okay, let's go to the collection view. So what you're looking at here is the equivalent of 4 SQL tables in ArangoDB. These are just called collections. The graph entity collection serves as the place where all of the nodes have been extracted by the large language model, and your embedding is over here. Then you have, of course, your source collection, which is just the chunk itself and the embedding. And then you have your edge collection, which points from one entity to another. And then you have your second edge collection, which refers to one entity is part of another chunk or multiple chunks. From a query perspective, it's just a matter of applying functions such as cosine similarity or approximate cosine similarity as a function based on your scaling purposes, and then just creating a vector index on the collection so that you can make use of vector similarity at scale. All right, let's go back to the slides. I think at this point, I'll just quickly mention that so far it's been an amazing experience working with OPEA. Just to name a few people: Arun, Rita from the